So let's see, we're in the Vectorization Advisor session. My colleague Kevin O'Leary is going to be presenting. If you were fortunate enough to be at the lab yesterday, it was really hot in there and really crowded. But again, we got some really good feedback, and what Kevin's going to do is going to walk you through this new feature that was added to our Intel Advisor XE tool that released in 2016 this past August. And also, we'll keep our ears open for good questions, so please, ask questions as Kevin goes through, and if you do, you'll get one of these books. So, all right, actually, we have 6 of them to give away, so, so anyways, ask great questions, and with that, I'll turn it over to Kevin.
Thank you, Mike. As Mike's mentioned, my name is Kevin O'Leary, and I am the lead technical consulting engineer for Advisor and for our inspector tool. So Intel Advisor XE has been around for a few years, and before 2016, it was focused basically on thread prototyping. So it basically allowed you to find places in your code where you could parallelize your code by adding threads. And once you did that, we provided annotations that let you model that thread performance. So in 2016, we basically added Vectorization Advisor to Intel Advisor XE. And why? Vectorization is hard. I mean, Advisor XE was put together to basically help people add threads, but a lot of the feedback we got from our customers was something was missing. The tool didn't provide any assistance with vectorization. And again, the challenge, vectorization is complex. And our customers were having a hard time doing this. And again, vectorization is not a nice to have, it's a total requirement to get performance on your system. So this graph basically shows why it's a requirement. So that line you see way down the bottom looks kind of like looks like it's the final line there. That's the serial performance. The yellow line there is the vectorized performance, and then the gray line is threaded, and the green line is when you add threads and vectorization together. So 179 times performance, that's nothing to sneeze at. Again, this is what's possible to achieve when you vectorize and thread your code. So this talk is about Intel Advisor XE, basically focused on the vectorization portion of Intel Advisor XE. There's a lot of material online that discusses a lot of these features. This talk is basically brand new for this conference. I've really tried to go through and try to provide some methodology on how you would use the tool and how you would some of the key features and some of the key insights that it could provide. But if there's any questions, again, Mike's giving away free books, so definitely feel free to stop me anytime. We have a very small crowd. I'm really happy to make this as interactive as we can make it. So again, on the right-hand side, you see some of the reasons why we put together the threading portion of Advisor. People were trying to add threads to their applications, but they really weren't seeing the performance gains that they expected. Or they hit a scalability barrier where the code seemed to increase its speed, but as they went to faster and faster processors with more and more cores, the performance seemed to level off, and they weren't sure why. So in the threading portion of Advisor, you get all that feedback. You basically know where your code is going to max out based upon the threads you're adding. And that's probably all I'm going to say about the threading portion of Advisor, but I would encourage you to look at that tool as well. So on the left-hand side, Vectorization Advisor was put together to solve these problems. So customers were basically using these compiler flags. They were compiling for the new vectorization instruction sets. But again, they weren't seeing the performance gains they expected, and they weren't sure why. They weren't sure where to start with vectorization. The problem can be daunting, especially when you have a legacy application and you know you have to vectorize. But again, when you start using these compiler flags, you're not seeing the performance you expect. A lot of times our customers, they use part of the compiler called intrinsics. So they compile directly using compiler intrinsics to the lowest level instructions. It's very difficult to do, and it's very difficult to make it maintainable, because a couple of years later, they'll come up with some new vector instructions. So then you have to do all your work over again. So that's definitely, it can be helpful, but it's not the final answer. Finally, the Intel compiler provides really, really good vectorization reports. So if you've ever used the Intel compiler, they provide tons of useful data. If you compile with the vectorization reports on, you'll see a lot of useful information about what's been vectorized, what hasn't been vectorized. But the trouble is, that's all static information. So if a loop hasn't been vectorized, you don't know how important that is to you, because you don't know how much time you're spending in the loop. So Vectorization Advisor was meant to handle all these cases here. And I'll show all these cases one by one and describe them. So this is what you would see when you do the simplest survey inside of Vector Advisor. So the first step in Vector Advisor is to run a survey of your application. So what that would do is it would tell you exactly what loops have been vectorized and what hasn't been vectorized. So if you wanted to focus on unvectorized loops, click of a button, you would only see the unvectorized loops. And not just what's been vectorized and what hasn't been vectorized, how much time are you spending in those loops? So what loops are hot? The key to any performance optimization is focus on where you're spending your time. So in addition to where you're spending your time, for vectorization, we go one step further. We actually give you your trip counts. We tell you how many times you're iterating in your loops, what the minimum, maximum, and median is for those iterations, how many times your loops are called, and how long each iteration is taking. So all that is critical information, and I'll describe why it's so critical a little bit later. But suffice to say, trip counts are really, really critical for vectorization. So the next column over there is, if something hasn't been vectorized, why not? What's preventing this loop from being vectorized? In addition to what's preventing it is, give me a recommendation to help with this situation. So with anything, it's one thing to say, okay, I can't vectorize this loop, but what is the step to make me be successful in vectorization? So moving down to the bottom column, in your loops that are vectorized, that's not enough information. Okay, they're vectorized, but how efficient is the vectorization? So we can tell you exactly how efficient the vectorization is. Is it 100% efficient? Is it 50% efficient? We provide some really useful metrics for vectorization. And finally, we give a lot of useful information about what vectorization instruction set are you using? Are you using the one you expect? Are you using AVX2, AVX? That's very important, because a lot of times, if you are on a legacy application, you might not be able to make use of the latest vector instruction sets, but it's important to know which instruction set you're compiled for. So I mentioned that we give you information about why no vectorization, but we also give you information about, if your loops are vectorized, are there any issues that we can see that's preventing you from being vectorized efficiently? And again, the key point here is you want to focus on the loops that are hot. A lot of times there can be some very simple things that you can do to improve your efficiency or to vectorize your loops. A lot of what I'll be discussing here in this presentation are basically low-hanging optimization techniques that you can follow to try to improve your code. So before this presentation, I put together a methodology, and I basically say we have 4 steps. Now we have 5 steps. We've gotten better. So the first step is, what Vectorization Advisor does is it basically combines a dynamic analysis tool where we actually examine your code by running it and finding timing information about where you're spending your time. But we combine that information with the static information that was generated by the compiler. I've mentioned how useful the compiler reports are, but you could generate a lot of data, and sometimes that data can be hard to consume. So by bringing all that static information inside of a GUI like Advisor, you actually are able to scan through your code very quickly. So all that information the compiler is generating by scanning down the source tab of Advisor, you would see a plus sign on every one of your loops. And by expanding that plus sign, you would know exactly what the compiler did to that loop. Did it unroll the loop? Did it have anything special to say about the loop? All that information is available. And again, you can scan down that tab very easily. So I mentioned a couple times that it's not just enough to say, I can't vectorize this loop. We can actually give you some guidance about, if we detect a problem, we actually give you insights on how to fix the problem. Is your code not aligned properly? That can affect vectorization extensively. So we just don't say your code's not aligned. We basically say, okay, by the way, here are the directives you need to follow to align your code properly, and here are the pragmas that you need to follow to tell the compiler that it's been aligned. So actually, it's working hand in hand with you to improve your code. I've mentioned several times, trip counts are critical. That's step 3.
I do have a question.
Please.
Helping to understand alignment better. Okay, I understand the basic issue. Why can the compiler not align the code the data by itself?
The compiler is following the alignment that you specify for it. I mean, a lot of times the compiler may not know how you want something to be aligned. The compiler
be aligned to maximize performance.
Well, so what the compiler can do is it can basically generate different parts of your loops for the aligned portion of your code and the unaligned portions of your code. So it does its best to figure out how the code should be aligned, but unless you tell it exactly how you want it aligned, it's just going to pick. It's going to pick by its best heuristics to align your code. And again, it does do a good job of. I'm going to go into this a little bit more. It generates different artifacts for the parts of your loop which are aligned and which parts aren't aligned. A lot of times that unaligned portion could be very, very small. So it might not be an issue, but Vector Advisor will show you how much time you're spending in the unaligned portions of your loop. That's a good question. So step 4 is one of the common issues that causes your loops not to be able to be vectorized is the compiler detects dependencies between your iterations. If there are loop carry dependencies, in general, the compiler needs to treat each iteration as something that can be done independently. If that can't happen, then it basically says there's an assumed dependency. And that assumed dependency, in general, can prevent vectorization. Again, the compiler is static. It has to assume, based upon the semantics of the language, if it's possible for there to be a dependency, it has to assume there is a dependency. But what Vector Advisor is combine static with dynamic information. It can run your code and check all the memory references in your loop, so it can guarantee that, well, it can prove whether there's a dependency or not. So by running your code dynamically, getting that information, you can verify this assumed dependency is not real, and you can safely add a pragma to your code to vectorize that loop. So that's something that really can't be done statically. So step 5 is memory access pattern analysis. So a lot of times, even if your loops are vectorized properly, they might not be vectorized efficiently. And sometimes, or quite often, that how you've laid out your data structures are not vector friendly. So if you're iterating through your loop, so you're not iterating unit stride, or you're iterating constant stride, or mixed strides, all those things can affect vectorization. We've added an analysis called memory access pattern analysis, which can run your code, check your memory patterns, and tell you if you're doing things vector friendly. This is a little bit of kind of expanding what I was saying before. The top part of the screen there is basically showing you all your loops, all the characteristics of the vectorization of all your loops. And then the bottom part of the screen is showing, in this case here, it's showing a source tab, but that middle bar there lets you change what appears in the bottom part of the screen. In this case here is the source tab I've mentioned. You can scan down quickly, and by using those plus tabs, expand all the compiler messages, but you also have the ability to click on top-down. By doing that, it will show you where the loop that you're highlighted on, where it exists in the context of the rest of your program. Is it an inner loop? Is it an outer loop? If it's an outer loop, in general, the compiler won't always vectorize those loops. It's very conservative with vectorizing outer loops. So, but if you have a case where it's important for that outer loop to be vectorized, again, you have the ability to control that by using pragmas. A couple of the other things inside there, loop assembly. You can actually see what instructions are being used inside that code and how much time you're spending at that level. Again, recommendations. There are several ways to access our recommendations. Under the vector issues column, there are hyperlinks there which will point you to the recommendation, but also if you click on that recommendations tab, it will move directly to the recommendation. So, for example, I've mentioned assumed dependencies. If you clicked on the recommendations tab for the assumed dependencies loop, what it would do is it would say it needs more information, because until you've run a dependency analysis step, it doesn't know for sure whether there actually is a dependency. I mentioned how important vectorization is, but it's not just vectorization, it's vectorization efficiency. And this slide here is basically showing you what Vectorization Advisor can do for vectorization efficiency. So we'll show you what efficiency you're currently achieved. In this case here, it's 13% efficient. It's actually less efficient vectorized as opposed to scalar. So again, vectorization doesn't always improve your speed up. The upper bound for efficiency it's a percentage, so the upper bound would be 100%. So imagine if I was vectorized and my vector length was 4. So the most you could achieve is 4 times speed up based upon a vector length of 4. If you've achieved that 4 times speed up, you're 100% efficient. Again, in this case here, the first naive thing that we did was we added a pragma to force vectorization, and that actually slowed down the code. So all these things factor in to your vectorization. So it's important once you've run Vector Advisor to look at the vectorization efficiency and see where you have opportunities to increase your vectorization. I'm going to mention some of the steps you can take to do that. So I've mentioned a couple of things here, but I want to go through a little background on loop vectorization. So in general, when a compiler vectorizes a loop, it generally creates several different parts of the loop. The first part is the main vector body. That generally consists of your fastest portion of the loop. This is where the intense vectorization occurs. And this is really where you want to be. You want your loops to be executing in that vector body for most of their time. So next is an optional PO part. So if the compiler detects that you're using unaligned accesses, it will optionally generate a PO part. So usually it will use either scalar instructions for this PO part, or it can also generate slower vector instructions for that PO part. The next part of the loop is called a remainder part. So if your trip count is not divisible by your vector length, then you're going to have a portion of that leftover, which gets put into a remainder loop. So it's not able to form a complete vector because there aren't enough elements to form a complete vector. So that leftover part gets put into a remainder. In general, those use either scalar or slower vector instructions. So the reason why, please.
Yeah, I have one question regarding the size of the loop. If you have a way to set your loop size, let's say,
Yes.
what do you advise? I mean, which multiple of the vector length do you recommend?
As long as you're divisible by the vector length, that's preferable. So there are pragmas where you can actually set the trip count. And those can be very, very helpful. There are some other techniques which we also recommend that I'm going to get into in the slides, but you can pad your trip count so that it is divisible by the vector length. And that is, it's kind of counterintuitive because you're adding iterations of the loop. But if you can form a complete vector, that will increase your efficiency. And since we're doing these SIMD instructions, we're executing these things much quicker than the individual iterations would be executed. But we'll go into some of those low-hanging optimization techniques in a couple slides. Thank you. So I'm going to go through some problems here and just try to solve some issues with vectorization. So in general, step one, for unvectorized loops, try to figure out what's preventing the code from being vectorized and get tips on how to vectorize it. And so the step one would be looking at, after you've done a survey, clicking on unvectorized, checking out what portions of your code have not been vectorized. I've jumped right to the section about the survey tab inside of Advisor, but we also have a summary tab. We actually show you exactly how much time you're spending in your unvectorized, vectorized, and actually outside of any loops in general. So you actually know by running Advisor how well you're doing. But in general, if you're spending a lot of time in the unvectorized portions of your code, fixing that is generally step one. So once you have a better understanding about what's vectorized, what hasn't been vectorized, the second step is just try to increase the performance of your vectorized loops. So basically, going through the loops one by one and actually seeing what is the vectorization efficiency of those vectorized loops and getting tips on increasing that. So for both vectorized and unvectorized loops, memory layout is key to increasing your performance. And again, the step there would be to run a memory access pattern analysis to try to figure out how you're referencing memory. That last step there can be quite a big ask. I mean, basically, changing the layout of your data structures is not an easy task, but going through and using some of the common paradigms for vectorization, converting arrays of structures to structures of arrays, for example, that could be time well spent. In general, we do have specific recommendations, and we actually highlight some of those issues directly when you use Vector Advisor. So we can actually tell you, you might want to run memory access pattern analysis because we think there's an inefficient memory pattern here. So again, as a methodology, there are several categories to your loop. So the first category is this loop is vectorizable, but it's not currently being vectorized. So it can be quite easy to add pragmas to those loops to force vectorization. You might want to run some of the steps to prove that it's safe to vectorize, but once you've done that, adding those pragmas can allow the compiler to vectorize and show you if they're being vectorized efficiently. The second category is vectorized loops whose performance could be improved. So if you go in and you see a low vectorization efficiency, there are some common low-hanging optimization techniques that you can use, and we'll go through several of them. But the next category is vectorized loops whose performance was limited by data layout. And I've said several times, please.
Just one question, going back to the first item, vectorizable and not vectorized loops. Did I understand correctly? You said you may want to try sometime, or may want to try a couple of times to see if this directive is safe?
Well, so.
Because the compiler should know, right? I mean, at least the compiler should, if it would be unsafe,
Well, the compiler sometimes has to assume, the compiler has to be very, very conservative. Yes. So, and the compiler is static, so the compiler doesn't know the stuff that we can get from running your code dynamically. So I've mentioned previously The dependency analysis can prove that, there are no dependencies, but that's just one factor that can be preventing something from being vectorized. So for example, out-of-the-loop vectorization is another example of something where the compiler could vectorize that loop, but it may not choose to unless you tell it to.
Okay, so so you know that the loop's vectorizable, but the compiler would not classify it.
The compiler might not classify it as vectorizable because it doesn't know things like trip count, for example.
Because sometimes the compiler will also say, oh, not vectorized because it wouldn't be efficient.
Exactly.
So that's not one of them.
Well, but again, if the compiler doesn't think it's efficient, you can still force that to be vectorized, and then Vector Advisor would tell you what the efficiency is. If the efficiency went down, then you can perhaps remove the pragma. But there's a lot of techniques you can follow in there. Please.
Are you going to go over the difference or introduce the sim pragma versus the IVDEP pragma?
I can mention that briefly.
The reason I'm asking is in Fortran I understand why one would be preferred over the other, but I'm thinking for C, is IVDEP ever useful in C?
So when you say pragma SIMD, you're basically saying, I want you to vectorize this code, and trust me, it's safe. I want you to just do it. So if you do that, you will, if you do that and it's not safe, you will generate incorrect code. I mean, because the compiler will trust you, and it will do exactly what it's a directive to the compiler. Vectorize this code. If you have a reduction in your loop, doesn't matter. It will take your word for it. It's safe. IVDEP isn't that blunted instrument. IVDEP will basically say, I understand you want me to vectorize this code. I'll try to make it happen. If it can't do it legally, if it thinks there's something that's preventing vectorization, it won't do it. So that's the difference. A lot of times, naive users will go in and use pragma SIMDs all over the place, and that is not the approach, because again, if you do it haphazardly without knowing something is safe, that's the worst paradigm to follow.
And do you improve the output of, let's say, the feedback of the tool when you put, for example, IVDEP, you see that there is a dependency but a wrong dependency, and you don't know why using IVDEP it's still not working, and you really need to go to the SMD directive. Sometimes it's not so easy to understand why you need to put the SMD.
Well, in the case of an assumed dependency, the compiler might have something in there where it basically said it really thinks there is a dependency in there. By using a pragma SIMD, that would force the issue, and it would get rid of that. But using a tool like Vector Advisor to actually go in and actually verify that dependency didn't exist, that would be the recommendation there. But I'm not sure of a case where an assumed dependency would not vectorize with IVDEP. I believe that. I believe that. I don't know what specific case there is for that.
But as you said, I mean, you really need to be sure, because once you use a SIMD directive, then even if it is a wrong code, it will run with the vectorization and happen with that.
No, I've done that several times, and again, a lot of times naive users do that, and that's not what we should be teaching them. We should be teaching them they have to be safe. They actually have to know before they start giving this directive. And you can do this by code examination. I'm not saying code examination doesn't work, but code examination is also, it's quite difficult. You know, going through your loops, if they're complicated, it can be a big task with proving that to yourself that it's safe to do.
The compiler will point you to the dependence, right? That prevents
It will show, the messages in the compiler have gotten quite good. And I was mentioning before, these vector reports, these op reports, they are quite good, and they'll show you what it thinks the dependency is, the anti-flow, and but again, the compiler is static. By running Vector Advisor as a next step, you can actually have a dynamic tool that actually can check all references of memory. This dependency analysis, we actually can track every write and read of memory. So that step can be a large overhead because since we're mapping each load and store of memory, but it can be well worth your time just to have that extra confidence before you start using these pragmas. Sometimes you're spending a lot of time in that loop, so it's well worth your efforts to vectorize, and getting the feedback that it's safe is worth it. Okay. I think I was in the middle of this slide here. Vectorized loops whose performance was limited by data layout, I've mentioned several times. Again, that's not easy to resolve those. Sometimes it does require code refactoring, but in vectorization, code refactoring is sometimes required. I mean, having your data structures laid out properly in memory is critical. So just to add these two final categories, vectorized loops that perform well. If something's vectorized and vectorized at a high efficiency, in your case, I mean, you're done. I mean, if you have a lot of other loops that aren't vectorized or vectorized at a low efficiency, the ones that are highly efficient shouldn't be concerned to you. All other cases, including non-vectorizable kernels, a lot of times, some tasks, some algorithms are inherently difficult to vectorize. So, again, this talk is mainly concerned about finding opportunities to vectorize and to increase the vectorization. So I'm not really going to be concerned too much about these last two bullets. In this case here, I'm giving you kind of an example about all the loops presented in a program. I'm showing both vectorized and unvectorized. This is probably the first time you've seen Advisor XE. On the left-hand side, you basically have a list of analysis types that you can do. The first step, again, is to do a survey, and then to do a trip count analysis. We don't combine the collecting of trip counts with survey, and the main reason is in order to collect trip counts for your program, we have to add instrumentation to your code, and actually that does slow down your code. Survey is it's very, very low overhead. So we're trying to collect accurate time profiles for your program. So the survey data is showing you that time. Trip counts, again, is a second analysis type. By adding that that trip count, our vectorization efficiency metrics get much more accurate. So doing that trip count is worth the step. You'll see vectorization efficiency, but again, you'll see that number change potentially once you do trip count analysis. So
how do you measure the efficiency since it impacts the write time so much, this extra instrumentation? Are you able to kind of subtract the increased overhead?
So the timing data comes from purely the survey. So the trip count just goes, it affects the math of the efficiency, but it's not affecting the timing of the efficiency. So you'll see several columns inside of Advisor. You'll see estimated speed up. So you'll see what the speed up is, and then you'll see what the efficiency is. And again, the efficiency is based upon what's the potential for speed up, based upon your vector length. So then, once you've done the analysis and you have the lay of the land, what's happening in your code, you'll see you have the ability to do these further analyses, the dependency and memory access pattern analysis, but we don't do those for every loop in your program. We only do that for the loops that you specify. And the reason is there's a lot of overhead with checking all memory references. So there's a column here that allows you to select each one of these, any loop that you want, and perform the additional analysis. One thing I haven't mentioned is a lot of times people work in kind of a clustered environment, or they want to run using a command line and view the data using a GUI, and that's definitely available. So all these commands work in both command line and GUI mode. One of the buttons up here under the survey target, for example, you'll see a collect button, and that's how you would collect in the GUI. But there's also a command line hyperlink. If you clicked on the command line hyperlink, what that would do is that would give you the exact command you would need to run to do that analysis inside basically a terminal. So it's a little more complicated to do dependency and memory access pattern because you need to actually get a kind of a list of loops that you have access to. So what we do is we would tag each one of your loops with like a handle almost. So when you get that handle number, you can do your further analysis. And again, I would encourage you to go to the Intel Advisor XE website. That has a lot of information, a lot of really useful videos that describe a lot of what I'm saying online.
Are there some very simplistic tutorials there too?
Very, very. And actually, I'm going to be in the Intel booth tomorrow. Actually, I'll probably be there tomorrow, but I'm definitely going to be there Tuesday and Wednesday. If you'd like a demo of these features, I'm happy to give it to you. Yeah. But there are some intro tutorials and also some more advanced tutorials online and videos. Okay. I mentioned to get recommendations, you would either click on a hyperlink or you could also use a tab. And again, this is one of the key recommendations we've been working on recently. In this case here, Advisor is able to point out an inefficient memory pattern inside of your loop. And again, saying it needs more information to actually show what's going on. By running a memory access pattern analysis, you can actually see how you're striding through memory inside your loop. Any questions? So moving on to some of the categories that I mentioned. Vectorizable, but not vectorized. Our hottest loop falls in this category. In this case here, Advisor is reporting under why no vectorization. Vectorizer reports that loop iteration count could not be computed. It also gives details on how to vectorize this loop. It basically says you could use the OpenMP pragma SIMD to vectorize the loop. You could also use pragma SIMD to vectorize the loop. Or pragma ifdep would also probably vectorize the loop as well.
Did you say this is the advisor would tell you?
Yes.
If he knows, why doesn't, I mean, if the compiler knows, why doesn't he just...
The compiler is saying the loop iteration count could not be computed.
Okay. And then you feedback, oh, it's okay, it'll always
Right.
be greater than -1.
Right.
So go ahead and...
Well, again, a lot of this is also, it's giving you recommendations, giving you guidance. It's not saying that this is the be-all and end-all. It's saying to vectorize this loop, our recommendation is to try this pragma. So in this case here, I went through and did this, and I was actually able to vectorize this loop at 100% efficiency. So now, as I mentioned with my categories, this loop could now be moved to category 4. It's now a well-performing loop. We should move on to some of our other less performing loops. Again, category vectorizable but not vectorized. In a couple of my loops, the third loop I'm showing here is not able to vectorize this because an assumed dependency is present. Again, statically, the compiler thinks it is a dependency, but if I click on the recommendation tab, the recommendation is to confirm the dependency is actually a real dependency. So by going in, selecting that loop, and running the analysis for dependency analysis, I can prove if that dependency exists. So just kind of step back a little bit. Data dependencies are a tough problem for vectorization. So again, your iterations have to be independent in general to be vectorized. The compiler can be pretty smart about trying to get some of this stuff to vectorize, but it might not be able to do it efficiently. And as someone's mentioned, if the compiler can't do something efficiently, it might not choose to vectorize it at all. So again, it's worth your efforts to prove these dependencies are real. You'll know by running Vector Advisor if it's worth it based upon how much time you're spending in your loop. If it's a hot loop and an assumed dependency is present, then that will be one that would definitely be worth be worth your efforts. So how would you do this? So basically the step is to select the loop in that teardrop column, and then click on Check Dependencies, and then the Vector Advisor would come up with what we call a refinement report. The only reports I've shown you so far have been survey reports. We have two other reports that we put under refinement category. One of them is dependencies, and one of them is memory access patterns. So what we would do is we would check all the references of memory, and we would basically show the lines of code that you have a dependency. If you have a read dependency, read after write dependency, write after read dependency, or write after write dependency, we would show you exactly if it found dependencies in your code. So it's not just giving you a diagnostic, it's actually showing you the read in the write. And again, all these categories of dependency would make this loop not a good candidate for vectorization. You would generate incorrect code if you chose to vectorize this loop. So finally, well, not finally, but this next category is vectorized loops whose performance could be improved by low-hanging optimization techniques. In our case, my top two hot loops now fall into this category. They're both vectorized, but there are issues being reported with the vectorization. In both of these cases, they both have the issue ineffective peel remainder loop being generated. The top loop, it has no vector body. All it has is a peel loop. I think in this case, my trip count for this loop is pretty low, and it might not have felt that it had enough iterations to put in a vector body, but regardless, since it doesn't have a vector body, it's not going to be efficient, even if it is vectorized. The next loop, it has a vector body, and it has a peel, and it has a remainder, but it's only 27% efficient. So for this case, someone's mentioned alignment before, but aligning the data to prevent, aligning the data to remove the peel loop, and again, the second recommendation is adding padding to your iterations and adding padding to the data structures can basically remove that remainder loop. And again, in my case, by doing those things, I was able to increase the efficiency of this particular loop. So again, low-hanging optimization techniques, simple code transformations by aligning the data, telling the compiler the data is aligned, padding the data structures, padding the iterations so that they fit, so that they're divisible by the trip counts. In my case, I didn't tell the compiler what the trip count was, but there are pragmas to basically tell the compiler exactly what the trip count is. If you know that, adding that information can help the compiler remove those remainder loops. In my case, by doing some of these transformations, I was able to transform it from 27% efficient to 99% efficient. So now my speed up is 3.98 compared to 1.09. So when you see that speed up is relative to scalar code.
Of course, then you also make it dependent on the input data, right?
Right. So it's well. So yes. So if your loop counts are dependent upon input, then obviously you're not going to want to give that private. A lot of times the reason why the compiler can't know some of these things, because if you are dependent upon input, then in some cases it might have to have a peel loop, but in some cases it might not be necessary. But it's still going to generate them regardless.
But it'd still be good to give a loop count, because if I tell the compiler there's going to be a lot of them, wouldn't that be useful information for the compiler, or does it actually need to have an actual loop count?
The compiler doesn't need to have an actual loop count, but if you don't want the compiler to generate a peel in a remainder loop, then it's helpful to know the trip count for the compiler, because once it knows the trip counts, then that is static. It knows what you're telling it, that it's not going to need to generate these two other loops because it has enough information to make that calculation by itself. Again, the reason why this is so important is sometimes your trip count might be really, really low. I mean, if you don't have enough trip count to fit in a vector, then again, even if it can vectorize that, it's not going to be efficient. So that's why getting information like trip counts, and obviously you can go in your code and add print statements and know what the trip counts are.
So if I tell it a trip count, it's
right.
going to assume that trip count is exactly correct.
Correct.
Is there a way to tell the compiler, I know that this is going to be a large loop? Because essentially what I'm saying, or a small loop, I may not know whether it's 2 or 3, but I know it's probably not worth vectorizing. I may not know the precise loop count, but I know it's going to be very large.
Right.
Is that worthwhile information for the compiler?
I'm not sure it has heuristics like that. But there might be. My focus is not 100% on the compiler. My focus is mostly on the Vector Advisor. In your case, what I would probably do is use some of the primitives to say, you must vectorize this loop. So even if some of your heuristics say don't vectorize it, it might assume that it doesn't have enough trip count. But again, if you tell it that it should vectorize it, my guess is it will do that, and it will generate all those pieces that for the parts that aren't fully vectorizable.
Can you tell the compiler not to vectorize?
Yes. You can basically say, don't vectorize this loop. I think it's probably pragma no vectorized. I think I'm getting close to my time, I think. I'm going to go quickly through these last couple slides. Again, I've mentioned this several times. This is not an easy task, refactoring your program so you're changing your data layout, but we have recommendations specifically that point to issues based upon inefficient memory access. And again, the step would be to select the loop. And again, some of these issues, non-strided access to arrays. In this case here, it's pretty simplistic, but I'm incrementing by 2 rather than by 1. The bottom case, I have an indirect reference to, inside of an array. Notoriously hard to vectorize. But again, selecting those loops and checking memory access patterns would give you specific data about how you're accessing memory, whether you're accessing unit stride, constant stride, or mixed strides. So all those things are critical for vectorization.
Will it point you to any sort of alignment issues?
We do have information about alignment as well. And again, a lot of that factors back through the PL information. So I wanted to mention these last 2 slides here. If anyone is working on KNL, this tool does work on KNL right now. So you actually can do a survey and get information about AVX 512. So in this case here, it's showing you information specifically about AVX 512, some of the performance metrics related to AVX 512, what speed up that you're getting based upon the larger vector length, and what performance optimization problems and how you would fix those problems. This is an experimental feature that this is probably be my last topic I discuss. Again, for AVX 512, a lot of people know that they want to move to AVX 512. They know they want to move to KNL, but they don't currently have hardware. We have a feature that's currently experimental. If you're interested, we can provide access to this feature. What you can do is you can tell the Intel compiler to generate both AVX2 and AVX 512 instructions, and then run your survey inside of Advisor. So even though you're getting timing only on the AVX2 portion of the code, because that's all you have in your target, we also can give you insights on AVX 512, even though we're not currently running that. So again, this is experimental. If people are interested, please come see me or send email, and we can enable you with that feature. So again, in conclusion, modernizing your code is one of the key parts of this conference, and Vector Advisor is a key portion of that. So again, I have about a minute, but any questions, or if anybody likes the second part, I can definitely enable you with some of these experimental features. Thank you very much.